Okay, welcome to Princeton, welcome to the Institute. Thanks to the organizers for giving me the opportunity to give this talk. And this is a talk based on some work that we're working on. It hasn't appeared in the archive yet. And first, let me give you some very general motivations. So I'd like to point out some problems and some issues. So one question that we would like to understand is to understand better classical field theories. So classical weakly coupled, by classical I mean weakly coupled field theories that then we'll take this classical theorem, quantize it, and with a very small coupling. The question is, what are the possible Lagrangians? What are the possible classical equations we can write for these theories and classical action? And in particular, this problem for particles with spin is quite non-trivial. In fact, we are all familiar with the fact that with spin 1 and spin 2, to leading order in derivatives, the action is uniquely specified. So that shows the problem is quite interesting. And this problem can be studied in various ways. You can try to write down classical Lagrangians and then check that they lead to a unitary field theory. Or you can think about on-shell amplitudes and demand that they are unitary and crossing symmetric and Lorentz invariant. Now, there are some questions which are in this type of category. So the first question is, what is the most general form of a pure gravity theory? So imagine you have a theory that contains only massless gravitons. And if we restrict to leading order in derivatives, then we have the Einstein theory. But imagine there are higher derivative corrections, which are still important in the classical regime. Later we'll see what this means in practice, but that are still important. So what kind of higher derivative corrections can we have and still have a well-defined classical theory? This is a question whose answer we don't quite know. You can certainly write actions like that contain the Einstein term, so square root of GR, and perhaps some R² corrections. And those are some classical actions. Some of these actions have problems with ghosts that lead to particles which have a negative norm. Some other actions don't have this problem. So for example, there's a popular one which is called the Gauss-Bonnet action, which contains the Einstein term plus a particular R² term. And that seems fine in terms of quantizing the theory around flat space or around any curved background, which is a solution of the equations. So that's an example of a theory. But we don't know what the general constraints are. And in some of those theories have problems around specific backgrounds, but there we don't know whether the problem is with the background or with the theory itself. Another question we can ask, which is a close relative, is what is the most general form of a classical gravity theory, which can contain mass equal to 0 gravitons, but also maybe massive higher spin particles? So that's some other theory we would like to understand. String theory is a version of this. It's a particular solution to this question. But we'd like to understand what the general answer to this question is. Is there an answer which is not string theory, for example, of this question? And a closely related question is, what's the general classical theory for interacting massive higher spin particles? For example, the type of theory we get if we have large n QCD. So in the large n approximation, the coupling between, in the large n approximation, we expect to have glue balls, and that these glue balls are weakly coupled, have a coupling which is proportional to 1 over n. And if we understand, and so it should be in some sense classical. And the question is whether we can understand the constraints on the interactions of those particles, and perhaps a constraint on the spectrum of these particles, and so on. This is the type of question that led to string theory, so trying to understand consistent theories of interacting higher spin particles. And it was found that string theory is a solution. The solution was a simple string theory in 26 dimensions. Then people found solutions for string theories in 10 dimensions, superstring theories in 10 dimensions. But we still cannot have very effective methods for solving the original problem, which was that of a theory in 4 dimensions, a 4-dimensional theory of interacting massive higher spin particles. And duals of large N field theories in 4 dimensions should be such theories. So this is a version of, so this is trying to understand the structure of string theory just purely from the space-time point of view, and from the space-time point of view what we have is this theory of massive higher spin interacting particles, with or without a massless graviton. So we can have situations where we have a massless graviton, and situations like these ones where we don't have the massless graviton. So we know string theory is a solution, and we could wonder whether it is the only solution or which other constraint should be imposed in order to have a single solution. So in the same way that we understand now that general relativity is the simplest solution with massless spin 2 particles and leading order in derivatives, we'd like to understand whether string theory is unique in some way. Or if it's not, then find the most general type of theory of this kind. Now these are very old questions. These are questions from the 60s. And it's good to remind oneself of these questions. And I thought you should hear these questions. I don't know the answer to these questions. I don't know how to solve them, but maybe some of you will figure out how to solve them. Now, let me emphasize why we care about these questions. So, first of all, trying to understand this problem at the classical level is simpler than the generic quantum problem. And here by classical, again, I mean a weakly coupled at energies under consideration. So a theory might be weakly coupled at low energies and might become strongly coupled at high energies. But here we're trying to constrain the theory at the energies where it is weakly coupled, right? So, and the claim will be, and we'll see in a specific example later, that there are non-trivial constraints even when the theory is weakly coupled. And this is the question that I find most interesting. So one question that I find interesting is how unique is the structure of string theory? Perhaps can be understood if one understands the solutions of these questions. And finally, another example why this type of questions is interesting is to consider the holographic dual of a large N theory. So we know that the coupling is small by large N arguments. So the coupling in the bulk theory should be 1 over N. We know the stress tensor gives rise to a massless graviton in the bulk. And the question is, what are its interactions? Are the interactions between these particles those of a local theory or not? And in fact, the emergence of bulk locality in these situations is something that should be purely understood at the classical level in the space-time sense. Because we are always at weak coupling. So even if we vary the Toft coupling, the space-time coupling is always 1 over N and always remains small when we change the Toft coupling from weak to large. So understanding better this question of interacting classical higher spin particles, and especially the massive ones, will be important for solving this type of question. So in particular, their interactions are probably constrained to the single particle spectrum of the theory. And an example is if you have higher spin particles that become actually massless, then you have extra gauge symmetries, and the structure of the Lagrangian becomes that of the so-called Vasiliev theory. And so that's one clear example. But as we take these masses and we make them larger, so the masses of the higher spin particles, one question one has is whether the interactions then reduce to the interactions of the Einstein theory, or do they remain complicated like those of the Vasiliev theory? So highly non-local as the ones of the Vasiliev theory. So we'll not answer any of these questions. So we'll focus on a simpler question today. That was general motivation, and I wanted to emphasize this question so that you have them in mind. But we'll ask a simpler question. We'll consider the simplest interaction we can have in a gravity theory, which is the interaction between 3 gravitons. So to lead in order, we have 3 gravitons, and the next correction is the interaction between 3 gravitons. This has the 3-point interaction between gravitons has 3 different possible Lorentz invariant structures. One is the one we get in the Einstein theory, but we'll have two others. And we'll argue that the theories that have the other structures actually have a causality problem if no other particles are present, so if we don't have other massive particles. And this causality problem can be solved by adding massive particles with higher spin. Okay. So the plan of this talk is the following. So I will review Graviton 3-point functions, all these three structures I talked about before. We'll discuss a certain high energy scattering thought experiment. And we'll see that this thought experiment can be viewed as propagations through certain shock waves. And this will lead to certain time delays or time advances, which are related to the causality problems. And then we'll discuss how this problem can be solved and why we need higher spin particles to solve this problem. And then we'll end with a fun application. Let's consider 3-point scattering amplitudes. So we imagine we have 3 on-shell particles, and they are interacting at the vertex. And in this situation, if we have particles of spin 0, these amplitudes cannot depend on any non-trivial kinematic invariant, because, for example, so all the ki's obey the Marshall condition, so their squares are 0. Let's say we are having massless particles. And if we take something like k1 plus k2, so we try to form this type of Mandelstam invariant, we'll get that due to momentum conservation, we'll get that it is equal to k3 squared, and it will also be 0. So that we cannot have any non-trivial invariant, and so we have a single constant, which is the coupling constant, and that's it. That changes a bit when we have spin, particles with spin. And so we can have now the polarization vectors of the particles with spin 1. And in this case, well, of course, these polarization vectors have to obey certain conditions, and we have the gauge invariant constraint. But taking into account these constraints, it turns out that there are these 2 possible structures. One is the amplitude we get in Yang-Mills theory. So this is the familiar 3-point amplitude of Yang-Mills theory, of non-abelian Yang-Mills theory. And this amplitude is one which we can certainly write down and is consistent with the Lorentz symmetry of the theory. And we get it from a term in the Lagrangian of the form f cubed, where this, for example, in non-abelian case is f cubed. And this amplitude relative to the previous one has 2 extra factors of energy. Okay? So if we scale the energies uniformly upwards, this one grows faster with energy than this one. Now if we do the same for spin 2, so we can view the polarization tensor of the spin 2 particles, so epsilon mu nu, as a product of 2 polarization vectors of spin 1 particles. And then we can write 3 different structures which were the same as that we had for spin 1. And so we can take the product of 2 of the ones were similar to the Yang-Mills structure, or 1 Yang-Mills times the second one, or 1 Yang-Mills times the f cubed one. And this way we generate 3 different structures for the Graviton 3-point functions. And these 3 different structures, we can get them from terms in the Lagrangian, which are, for example, the first one comes from the Einstein term in the Lagrangian. The second one comes from a Riemann squared term in the Lagrangian. That way we get the second one. And the third one can come from a term which is of the form Riemann cube in the Lagrangian. Of course, all these indices are constructed they are fully contracted. And these parameters here I've written the parameters here in front of these terms in the Lagrangian so that these parameters have dimensions of length. We pulled out an overall 1 over g Newton. And we're going to assume that g Newton is very, very tiny. So the coupling is going to be very small. So there is a factor of square root of g Newton in this 3-point amplitude. And this will be very, very small. Yes? the question is whether in the spin 1 we need structure constants. Yeah, indeed, this term is anti-symmetric in the particles. And so either we need 3 different U1 gauge fields, or we need some structure which is anti-symmetric in the. So if you have a single non-abelian gauge field, then we can write this, and there will be an FABC here in this term. But that is a detail. So when we go back to the spin 2 case, this is fully symmetric in the 3 particles, and then. So the previous 2 structures were anti-symmetric in the 3 particles. These ones are symmetric because we take the product of the 2, and so the 3 terms we are having are fully consistent with the symmetries of the gravitons. Now we have this. We write in the coefficients in this way. We have some overall coupling which is very tiny, and then here we have some dimensions of length which have some fixed length, so they are some order. And here I wrote this as a square, but this might be imaginary, so the sign can be plus or minus here. And I wanted to choose them in such a way that both have units of length squared. So we have this overall coupling, which is very small. And at distances comparable to these alphas, or momenta, which are 1 over square root of alpha, all these 3 structures are comparable and would give comparable contributions to the scattering amplitude of the 3 gravitons. But they are all small. So it's not that we can be in a regime where the 3 are comparable to each other, but all 3 of them are small. Okay? So that's why we were where I was emphasizing this classical limit. So we have a situation where the coupling is small, the theory is classical or close to classical, and but the 3 structures are contributing. Now in 4 dimensions we also have an even simpler way to describe this. So in 4 dimensions, it's convenient to think about, instead of thinking about the polarization tensors, we just think about the helicity of the gravitons, and then we can split the amplitudes according to their helicities. And so once we fix the helicities of the external particles, it turns out that the amplitudes are uniquely fixed. And so the plus plus minus and minus plus plus and any other combination of these pluses and minuses, but with 2 pluses and 1 minus, or this one, then that gives us the usual amplitude, so the usual Einstein amplitude, or in the case of spin 1, the Yang-Mills term. And the plus 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 and minus minus amplitudes give the new ones. In this case, they correspond to the ones that come from the R cubed term in the Lagrangian. And in 4 dimensions, there is a small detail, which is that you could have different coefficients for plus 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 and plus plus minus minus minus. And if those 2 coefficients are different, then we have a parity violating situation, and that corresponds to replacing one of the curvatures in this term by the dual. So we contract with an epsilon tensor and we take the dual one. This will not be important for anything else we do, but I just wanted to mention it. And the R squared term that we had in other dimensions, in 4 dimensions, is actually topological. And so this structure is actually not present, so vanishes identically in d equal to 4. So we can say that in this case, alpha 2 is equal to 0. Okay, so an example of a theory of this kind is perturbative string theory. When G is very tiny and alpha prime is finite, then in this situation, the Planck length is much, much smaller than alpha prime. And in fact, one can calculate those coefficients of the 3-point functions. And for various string theories, we get various answers. So in the case of the bosonic string, we can get that. Can you see the pointer? Probably not. So we have alpha 2 and alpha 4 are both non-zero, and of order alpha prime. And in the heterotic case, well, actually in any supersymmetric theory, alpha 4 has to be 0 by supersymmetry. And so the supersymmetric Bauer identities imply that the structure corresponding to alpha 4 is actually 0 and in any dimension. And then for the heterotic case, alpha 2 is non-zero, and for the type 2 alpha 2 is equal to 0. Yes?
The type 2 is the y alpha 2 equals alpha 4 and 0 is ruled out by supersymmetry? Or
Say again?
so I'm just asking y alpha 2 equals alpha 4 and 0.
Yeah, those are ruled out by supersymmetry. By the supersymmetry of the type 2 theory. Okay, but in string theory, there are also massive higher spin particles at these scales. So it's not that we get the modification of the 3-point function and nothing else. We get the modification of the 3-point function and also some extra massive particles, and in particular particles with higher spin at this scale. So this is just an example. Now here I would like to make another comment. So the size of the higher curvature corrections, so the size of the term in the Lagrangian that we are considering, is much, much larger than the value suggested by effective field theory as applied to the Einstein action. So when we think of the Einstein action and treat it using the formalism of effective field theory, we would guess a natural term for the R² term, which has a coefficient of order L Planck squared. So in some sense, effective field theory gives you the minimum value that this term should have. That's when we put the cutoff, or the theory is just gravity up to the scale proportional to, up to the Planck scale. In some sense, this is the minimum value these terms could have. But in our case, we are considering a situation where L Planck is much, much smaller than alpha. And so this term is much, much larger than the value that is natural in effective field theory. So this is the natural value we get if we take look at the one loop corrections, and we put this cutoff at the order of L Planck. Okay, so that's, I wanted to emphasize this because this sometimes causes some confusion when we're talking about this. So the values we are talking about are much larger, and indeed in string theory we have corrections to the Einstein action which are much larger than the ones we would naively expect based on effective field theory. Okay? So the correction to the Einstein theory doesn't come at the Planck scale, but it comes at the string scale, which for weakly coupled string theory is much lower. Okay, okay, so now we'll consider the following thought experiment. So we'll consider two fast-moving gravitons, so scattering between two gravitons at high energies. And by high energies, I mean an energy which is much bigger than the fixed impact parameter. So we're going to do the scattering at fixed impact parameter. So rather than fixing t, we are going to fix the impact parameter. And of course, then t will be of the order of, roughly of the order of b squared, 1 over b squared. But the energies are still, S is not so high that we are in the strongly coupled regime. So we want S to be low enough that we're in the weakly coupled regime. But still much larger than t. So we have a small angle scattering situation. And we will take this impact parameter to be of the order of the new terms that appear in the Lagrangian. So these are proportional to these new length scales that were appearing in the classical Lagrangian, or that were appearing in the ratios between the new amplitude and the old amplitude. So and we can obey all of these conditions. So we can take t to be large enough so that these new terms are comparable, in the 3-point functions are comparable to the Einstein term, and at the same time S very, very large, so that we can localize these gravitons in the transverse dimensions so that we can talk about this fixed impact parameter configuration. And also such that the theory is weakly coupled. So let's first discuss this in general relativity. And in order to describe it, let's view it as follows. So let's imagine that this first particle is fast moving and it creates a gravitational field. So let's view this as the gravitational field created by the particle. And so we have the flat space metric, and then the gravitational field is described by a metric of this form, where we have function h, which is a delta function localized in the x plus direction. So the particle here is one is moving to the left, is localized in the x plus direction, is moving at the speed of light. And then we have here a function which is a solution of the Laplace equation in the transverse dimensions. and well, with a value, with an amplitude which is proportional to the momentum of this particle number 1. And then we'll treat the second particle as a probe moving on this geometry. Now, in the equal to 4, this term has a log of r, or will translate in a log of the impact parameter. So the fact that it's a log is related, so it should be a log divided by some other length scale. The other length scale will be some big infrared cutoff. And so there is some dependence on this infrared cutoff, but this will not be important for us. So, or we could be in ADS where this log is naturally regulated by the radius of ADS. So in a situation like this, so this is the drawing of the previous geometry. So we have x plus and x minus, and then at x plus equal to 0, we have the shock that is created by the particle, the first particle which is moving along this direction. Now we have the second particle, and as it passes through this shock, it suffers a shift in the x minus direction, which is proportional to this same combination that was appearing in the metric. So let me briefly explain why we get this answer. So we go back to the previous metric, and we notice that this metric is very weird. It's discontinuous. This is a discontinuous metric. But we can do a change of coordinates, so a discontinuous change of coordinates that makes the metric continuous at the position where the particle number 2 crosses. And so once we have the metric written in that continuous form, then we expect that in that form of the metric, then the particle should cross without problem. Okay, should just simply cross in a continuous. The trajectory should be continuous in those variables. And then undoing that change of coordinates, we just simply get back to this result. So that's one way of getting this, but there are, of course, other ways of getting the same answer. This is a particular variation on a well-known effect, which is the Shapiro time delay that leads to the fourth test of general relativity. So you are probably all familiar with the fact that light going near the sun is slightly deflected. That was one of the tests of general relativity. But in addition to the bending of light, there is also a time delay, some time delay. And this time delay, of course, has been measured. The effect was noticed only in the 60s and measured later in the 70s, and recently with the Cassini spacecraft was measured even better. But this is a similar story, except that instead of having the sun at rest, we have a particle that is just moving fast, but it's more or less the same. And by the way, this effect involves a log, also here we're in 4 dimensions. And in 4 dimensions, this can be measured. There is no problem with these infrared diversions. So that shows you that it is not an issue. Now, in that case, you have the log of the distance to the sun, and the infrared cutoff has to do with the distance to the Earth or the distance to the other emitter. So this is related to the fact that gravity always sort of slows you down. So in fact, the null energy condition, so that is to say that T++ is always positive, plus Einstein's equations, implies that asymptotic causality is respected. So this is a quite non-trivial aspect of general relativity. So if you have some Minkowski space far away that defines some notion of causality far away, or some ADS far away that defines some asymptotic notion of causality, then by sending signals through the interior, you cannot get to the faraway region faster than you would have gotten if you had remained far from the interior region. Okay? That's roughly the way it's formulated by Jan Wald, who proved this result. And we will actually impose this as a principle for any theory of gravity. And in higher dimensions, it's in 4 dimensions, it's a little subtle to impose this because of this logarithmic term that we discussed before. But in higher dimensions, it's a simpler constraint to impose. And you can see that if you don't impose this constraint, then these little time advances or little violations of causality can lead to closed time-like curves if you consider two boosted observers. So one, to get a little bit of time violation in some reference frame, then you do a boost to, and then you consider a second one that is boosted relative to the first one, and then, well, I won't give that in detail, but that is true. Also in ADS, imagine that you had an ADS setup where we have the boundary theory, and you can send the signal from this point to that point through the boundary. So let's say we send the signal to here, and the fastest way a signal can travel is to get here at some time t. Then you cannot get faster by going through the bulk. Okay? So that's this notion that we are having. If you could get faster going through the bulk, then you would have a violation of boundary causality. So that would be a setup that would be inconsistent with ADS-CFT, for example. So it would be inconsistent with the idea that the dual is a ordinary relativistic field theory. And in fact, the null energy condition ensures that that can never happen. Now, if now we go and so that all that was in Einstein, the Einstein theory of gravity. And I said this asymptotic notion of causality is quite a non-trivial constraint on the theory. And in fact, it will be violated in the theories that contain these corrections to the 3-point function. So in fact, we can repeat this type of experiment in the theories that have the corrected vertex. And in those theories, we find that the correction has this form. So we get the 1 is what the result we got in the Einstein theory for the time delay. But then the other vertices lead to spin-dependent corrections, so spin-dependent corrections. And they were proportional to the momentum, and the momentum translates then into a derivative with respect to the transverse position. And so this leads roughly to an expression of this form. And depending on the spins we choose here, we can get plus or minus signs here. And so regardless of the signs of these coefficients, we will always get some trouble. So we can choose the spins so that we get the time advance instead of a time delay. So we get a situation like this where the signal actually arrives to the faraway position faster than it would have arrived in flat space. So we can have propagation faster than light as seen from infinity. And this then violates this principle of asymptotic causality. And if this was occurring inside ADS, it would violate causality in the boundary theory. Now, this whole discussion, I described it in terms of the shock waves to connect it a little bit with this Shapiro time delay discussion. However, it really depends only on on-shell 3-point amplitudes. So if we consider the leading order term in perturbation theory, so the leading order term that contributes to this effect, so we'll have the external particles. And if we look at the contribution at fixed impact parameter, the only term that can contribute at fixed impact parameter is the term that contains the propagation of a the propagation of an on-shell particle here along this channel. This is the same as saying that the only way we can get a long distance force in a relativistic theory is by the propagation of an on-shell particle with space-like momentum. Okay, so this is the only diagram that contributes to this point. And since this particle is on-shell, these 3-point amplitudes will be on-shell 3-point amplitudes. They were the 3-point amplitudes we were discussing before. One curious fact is that since this momentum is space-like, these 3-point functions have effectively kinematics which is similar to that of 2-time directions. So this space-like direction, we can view it as q, which is time-like in 2-time directions. And for that reason, these 3-point amplitudes are non-zero. Because with purely Lorentzian kinematics in 3+1 dimensions, or with only one time, these on-shell 3-point functions will always be 0. Another point is that all other vertices can be neglected. So this causality problem cannot be fixed by adding higher order terms to the Lagrangian. So it's not that we'll add some r to the fourth term and we'll fix this problem and so on. An r to the fourth term might give rise to a coupling of this form, but this coupling does not contribute at fixed impact parameter. So if we want to solve this in the classical theory, we really need extra particles that propagate here. So we need extra long-range forces that will fix this problem. Now then the full argument to say that there is a problem involves taking this leading order amplitude, which is an effect which is small, and then iterating it so that we generate a causality violation which is bigger than the quantum uncertainty in the time resolution of the experiment. So that's a small detail. So we'll add extra massive particles here, but if we have extra massive particles here, we'll also have them in the external particles and the external legs. But one can argue that these do not appear to solve the problem. So we'll really concentrate on the adding extra massive particles along this channel. Now, something important is that this the overall dimensionless size of this effect, of the time delay effect, really is proportional to S, to the Mandelstam, to the center of mass energy, square energy, the square of the center of mass energy. That is, so we have one particle which mainly has P plus, very large, and this one has very large P minus, that's S. And the graviton time produced by the graviton grows like S. Okay? Of all three terms, it grows like S. So the effect produced by the new particles should also grow at least like S. So if we have some effect which does not grow like S, then it will not be important at high energies, and we still have the problem at high energies. In fact, if we have here a particle of spin capital S, then the effect will grow like the Mandelstam variable S to the power S minus 1. And the way to understand this is that here we are propagating a particle with some polarizations. And the term that gives rise to this high power of S, or to some power of S, is a term that will involve a contraction between a P plus here and a P minus here. But here we're just simply having the 3-point function, so that contraction will not come from the 3-point function itself, but it must come from a contraction between the P plus and the polarization tensor of this particle. And then we have a polarization tensor of this particle here contracted with this P minus. And then we have a sum over all the polarization tensors. And that sum effectively will produce this contraction between P plus and P minus. Okay? But how many contractions we will have depend on how many indices this polarization tensor has. So there is a fixed number of indices that, S indices. So the most we can have in the amplitude is the variable Mandelstam S to the power spin S. Okay? So that's the maximum we can have. And then in the phase shift, because there is a factor of S which is purely kinematic, I'm not going to discuss, that is the minus 1. That's this minus 1. Okay, so we need, therefore, new particles with spins which are bigger or equal than 2. Okay? So we cannot fix this with having scalars being exchanged or spin 1 particles being exchanged here. Now, let's see what we can do with massive spin 2 particles. And first, we'll discuss now the 4-dimensional massive amplitude. So we'll have the red line is a massive spin 2 particle. And let's consider this massive spin 2 particle in the rest frame of the massive particle. So this particle can decay into 2 massless particles. And we can label the 2 massless particles by the helicities. So we have helicities which could be plus or minus on each of the 2 sides. But then, let's say this particle decays by emitting this graviton along the c direction, right? Then we look at the conservation of angular momentum around the direction of the graviton. And then then we see that this configuration is allowed because the total angular momentum is 0 because of the spins. And well, these massive spin 2 particles could be in a spin 0 state around that particular generator. Okay? And this one, which would be the minus plus amplitude, on the other hand, is not allowed because this would sum up to spin 4 along that axis. And this massive particle cannot be in a spin 4 projection on that axis because the maximum projection is 2. So only the plus plus or plus minus amplitudes are allowed because of this angular momentum conservation condition. Now this is the same argument that Weinberg and Witten gave, saying that there is no stress tensor in a theory of gravity. So we have a theory with massless gravitons. We cannot have a stress tensor. So in their argument, instead of having a massive spin 2 particles, the role played here by a massive spin 2 particles, in their argument was played by the stress tensor at some off-shell momentum, q squared. Okay. So now we can go back to our experiment, and on this side we can set up a coherent state of particles of a given spin. So in this case, we will not have a contribution from this spin flip amplitude. So this amplitude in this context will contribute only if if the spin of this particle is different than the helicity of this particle. So it's when you have a helicity flip. But if we set up a coherent state, the main contribution will come from particles where the spin is not flipping. So in this situation, we will not source the massive gravitons, but we'll still source the ordinary massless graviton. And then when we take the second particle propagating here, we'll have the problem that was created by the massless exchange of the graviton, but it cannot be fixed by the exchange of these massive particles. Okay? So this shows that this problem in 4 dimensions cannot be solved by massive spin 2 particles. Now if we have massive spin bigger than 2 particles, then the phase shift of the second particle as it crosses the shock will be a constant times, we were saying it will grow like s to some power, and it's a function of p minus. Then it's some function of p minus, and we'd like to understand what this function of p minus can be. Well, we know that it will be of this form, but what can it be if it is a causal theory? So p minus is like the frequency of the wave that we're passing through the shock, and causality implies that we should have something analytic in the upper half plane. So this looks like it's analytic in the upper half plane. But we also expect that it should remain bounded in the upper half plane. Also, we think we haven't derived it completely, but it should be constrained from causality because there are counterexamples. And indeed, if the spin is bigger than 1, there will be regions in the upper half plane where this phase shift, so this scattering factor, will increase exponentially. So this means that if you have a fixed number of higher spin particles, you will have a problem from the particle of higher spin. And so we could have an infinite number of higher spin particles with delicate cancellations between all of them, so that in the end of the day, nothing grows faster than s in the phase shift. And indeed, this works in string theory. So in fact, string theory is an example that contains all these particles, and this problem is solved in this way. So, and one can check this by taking the 4 graviton string 3 amplitude and take the largest limit. Then one goes to the impact parameter representation, and we find that this phase shift grows like s, actually a little lower than s, which has this suppressed by this logarithmic term. But in particular, the higher spin particles do not give something that grows with s, which just simply gives something that does not increase. And indeed, this phase shift also has the right sign to lead to a time delay. In addition, in string theory, something not going to be important for what I'm saying is that delta develops an imaginary part due to the possibility of exciting strings along the s channel. So we collide these 2 gravitons and we create a massive closed string that then can decay and so on. So the typical state will contain this excited particle, and it's unlikely that you just get only 2 gravitons back out, and that's why we have this imaginary part. Okay, so the conclusion is that if the graviton 3-point function differs from the one in the Einstein theory, then we get the causality problem. And in d = 4, to fix it, we need an infinite number of massive higher spin particles, and the masses of these particles should be roughly of this form. The actual constraint depends on what you assume about the coupling of the new particles. So if we assume the couplings are all equal, then roughly the masses where they should appear should be related to the coefficient of this 3-point function of the gravitons through this formula. In d bigger than 4, in principle, we might be able to solve this with an infinite number of massive spin 2 particles. We haven't shown that it is impossible to do this, but so maybe you could do that. We don't know that for sure. So, but in any case, you need an infinite number of new particles, whether spin 2 or higher. And in 4 dimensions, they have to have particle masses spins strictly bigger than 2. Now, let's try to understand where these corrections come from in string theory, just to understand the intuition for why we would expect to see a problem and why we expect to see a result of this kind. So if the graviton is an extended object, then when this is the graviton, it contains, let's say, 2 little partons. And when it crosses through the shock, let's say each parton has a phase shift that is similar to the one we get in Einstein theory. But one crosses at one position and the other one crosses at a different position in the transverse directions. And so we'll get the final phase shift, which will contain the second derivatives, which were of the kind that we find in the correction to the vertices. So in some sense, you can view the correction to the vertices as some indirect evidence of the compositeness of the graviton. Of course, if the graviton was composite, indeed, when you get to situations where these 2 terms are equally important, it means that the graviton got really split into two very different pieces, and so the graviton can be excited, and this is related to the presence of higher spin particles. So everything I said here was qualitative, but it's the intuition that allows you to understand why these 2 facts are connected. Now let me discuss now an application for the ADS duals of large n-gauge theories. So in this case, we have 3 different structures for the stress tensor 3-point functions. So here we have the stress tensor 3-point functions on the boundary, and they are dual in the bulk to graviton 3-point amplitudes. And in general, you can have these 3 different structures. If we have supersymmetry, we can have only 2 of them. So those 3-point functions also determine the conformal anomaly coefficients, A and C. So the trace of the stress tensor is not 0, but is equal to the Weil tensor on the boundary theory plus the Euler invariant, the Euler density in the boundary theory. And the 2 coefficients are called C and A conventionally. Now, if the bulk theory is described by Einstein gravity, then we get that A is equal to C. Now, if the bulk theory contains a correction to the Einstein term, in particular, let me just say the theory is supersymmetric, so we only have this correction, then A minus C over C is going to be proportional to this alpha 2 correction, to the term proportional to R squared. So it's the size of this length in units of the radius of ADS. That determines the deviation from the Einstein action. Now, we can now apply the analysis we did before to the region around this vertex, so this nearly flat space region around the vertex, and we will get the condition we derived before, that we have particles of spins bigger or equal than 2 at this order of masses, will imply, together with this condition between the dimension and the mass of ADS, that the deviation between C and A has to be lower, so the values of the 3-point function has to be lower than 1 over the dimensions of the operators which have spin bigger or equal than 2. Okay? So this is a relationship between between deviations of some coupling in the action to the spectrum of the theory. Okay? So if all the higher spin particles all have very high masses, then A and C cannot differ too much from each other. Now, it would be nice to derive this from the conformal bootstrap. So recently there was a lot of progress in understanding better the conformal bootstrap. And many of the techniques there used the external states which were spinless. And so here spin played an important role in these considerations. And it is likely that by doing similar things to the things that were done with particles or operators with spin, you might get extra constraints. Okay, now let me discuss a fun application of this. So let's scatter 3 gravitons at 10 to the 14 GeV. Okay, let's consider a 10 to the 14 GeV graviton collider. Now, h during inflation, so the Hubble scale during inflation could be this high if this bicep experiment is correct. We don't know whether it's correct or not, but if the bicep signal is primordial, then h could be this high. Maybe it's a little lower, but it could certainly be this high. Now, gravitons get produced by inflation with energies which are proportional to h, to the Hubble scale during inflation. The gravitons are weakly coupled. In fact, the 2-point function of gravity waves is of the form h squared over m Planck, and that is a measure of the effective coupling. Because these are the quantum fluctuations, it's telling us directly the effective value of h bar during inflation. And this is definitely less than 10 to the minus 9, whether the bicep experiment is correct or wrong. Just the fact that we haven't already seen gravity waves tells us that it should be less than this. So we are dealing with a very weakly coupled theory of gravity during inflation. Okay? Now, these gravitons can collide. So we can have these gravity waves, and they can collide with each other. And so these collisions can affect the statistics of these gravity waves and the statistics of the gravity waves we see in the sky. So in fact, there can be non-Gaussianities in the gravity wave distribution or spectrum of primordial tensor fluctuations. And in fact, you can calculate those. So in a purely Gaussian theory, the 3-point function would be 0. So these 3-point functions are ordinarily computed in momentum space, where you take you look at waves with specific wavelengths, and you consider this correlation, these 3-point correlation functions. So by translation symmetry, the sum of the 3 wavelengths should be 0. The 3 momentum vectors should be 0. These are momentum vectors in 3 spatial dimensions. And then you get that this 3-point function is a function of this triangle, and also a function of the polarizations of the gravity waves we are looking at. Now, so the size of the 3-point functions relative to the size of the 2-point functions is small, is proportional to the coupling. The coupling is h over m Planck. As we saw, that was small. And in the Einstein theory, we get a particular shape here. So I won't write it down, but it's a known shape. That is a function of the 3 momenta. Now, it turns out that the symmetries of the Sitter space, so if we approximate inflation by the Sitter space, then we have the scale invariance of the fluctuations, has to do with the time translation symmetry of the Sitter space. And we also have the conformal invariance of the wave function of the universe is related to the isometries of the Sitter space, all the isometries of the Sitter space. And those allow only these 2 possible shapes. So that is, with no assumption of what the dynamics of the theory is, we have only these 2 possible shapes. And if we had a term in the Lagrangian that was of the form r cubed, then we could generate certainly this shape with a size which is proportional to this length scale in units of the radius of the Sitter space, of the Hubble radius during inflation. So all this just follows from the symmetries. I mean, many other properties of the inflationary perturbations just that have been observed so far follow just purely from the symmetries of the zither. Okay, so we had this overall coupling, and this is allowed in principle. And so imagine that this allowed term is actually measured in the gravity wave spectrum. And so if that was measured, then it means that we have something like string theory during inflation. Okay? Because this is a term that was present during inflation. So if this coefficient is of order 1 or perhaps slightly less than 1, so but still measurable, then we had that implies through the previous arguments that we needed to have higher spin particles during inflation. Now the converse is not true, so that means the absence of this term doesn't mean that string theory is ruled out. Because we can have string theories with no correction to the Graviton 3-point function at the Hubble scale. In fact, most of the models that people discuss for string inflation, like the Ibren inflation or monodrome inflation, etc., are of this form, with no sizable corrections of the 3-point graviton at the Hubble scale, because in those models, they basically come from compactifying the 10-dimensional theory. We saw there were no corrections in 10 dimensions. In fact, in order to have a term like this of order 1, then you need the string scale to be, the string length to be comparable to the radius of the zither space during inflation. So it's not the type of model people ordinarily look at. It's perhaps not the simplest model building scenario because it's difficult to analyze such string theories. But if a string theory inflationary model like this existed and had this signature, it would be really drastic way to confirm or to see evidence for string theory. Because this is a structure we cannot, we've argued we cannot generate it in effective field theory with massless gravity plus ordinary particles. Okay, so conclusions are that these deviations of the Graviton 3-point function from the Einstein theory are inconsistent with causal field theories with particles with spin less than 1 in 4 dimensions. And it signals the existence of new higher spin particles if the theory is weakly coupled. And in the case of the gravity wave 3-point function in inflation, the theory is definitely weakly coupled. And if seen, it would be an indication of structures like we have in string theory. Okay, thank you.